All right, day 3 of limits. So we saw kind of at the end of our previous lesson that the tools that we have were not quite enough to deal with all of the limits that we're trying to do. So we need some other techniques that we can use in order to evaluate some more limits because just we don't have enough tools yet. We need more tools in our toolbox. That's what today is. I've got some sweet techniques to show you. So if you want to write all these down, we're going to be working through an example of basically everyone. These first two we've done already. You might want to pause here. Hopefully that was your pause. So we've done the first two. The ones we haven't seen yet are techniques 3, 4, and 5. So the direct substitution, that was the one that I told you at the end of our previous lesson video. So here's another example of us doing this technique. I'm not going to work through another one because it's pretty straightforward. If you have a nice polynomial, like you don't have any sort of denominator stuff going on, um, you can take whatever your limit is heading towards and just jam that number right into the thing. So take this -1/2 and just jam it right in there, and then whatever it evaluates out to, that is the limit. Now, this one, we've got a problem. So we have an x in the denominator, so we can't just direct substitution this thing. Now, this one is in your Larson book, but the Larson book is wrong. It's got like a delta t down here, and from what I understand, that is a typo. So it's got a delta t. Don't really worry about that. This delta thing, this is something that we're going to be seeing pretty soon here in calculus. I think it's next chapter. I haven't done next chapter yet, so I don't know for sure. But this delta thing is going to be coming. So I figured it'd be nice to see an example with it. We're going to do that same thing. Delta x is just a variable, just like x is. But just like x, I can't put 0 in the denominator. So I'm going to try to clean up that numerator a little bit. Now I'm going to keep this 2x and the two delta x's separate because the delta x and the x are separate variables, just like x and x squared would be, and just like y and y squared would be, or y and x would be. Now I've got some like terms in that numerator, so this equals 2 delta x. Oh, I forgot my limits. Sorry, don't forget your limits. That will cost you this problem on an AP exam, so don't you forget it. They won't forget you. Okay, so I've got 2 delta x over delta x. Sweet, lay to delta x's. So the limit as x approaches 0, delta x approaches 0, of 2 what is just 2. That was technique number 1 was saying if you're doing the limit of a constant, it is just the constant. So done. And again, textbook, it's got delta t. Don't know why. I think it's a typo. But we get 2. Plus the book even says it's 2. So yeah, hopefully you're getting similar things wrong. Now, here's something that the Larson book also wants to do so you can see why we're able to use this sneaky trick. So if we were to do this problem using Tech 3, we would factor our numerator, so we get x plus 1, x minus 1, over x plus 1. And these two things would cancel. So we get this new function. I forgot the limit again. My gosh, I am so sloppy. So we're trying to see how this limit is comparing to this limit of x minus 1. And you might look at that and you say, hey, those are different functions, so why are they approaching the same limit? Well, take a look at this. So I graphed them both on the same graph. In fact, actually, let me blow this up so you can see it. Now, I've graphed f of x and g of x on the same graph. So they're both here. So here's our original function that we wanted to figure out the limit of it. It's just a straight line. And then here's g of x. It's right on top of it. Now, you can even see if I type numbers into their table, like I can put in even more stuff. So if I put in like 7, the two functions are agreeing. 9, the two functions are agreeing, and they're behaving exactly the same. The only spot they're not quite working is that denominator, that troublesome denominator. At -1, they are not matching up. Now, for Tech 4, this is a funny one. So we can't factor that numerator. That's just not a polynomial that wants to be factored. And we also can't do direct substitution because we can't put a 4 there. So what we're going to do in this example is we're going to multiply the numerator and denominator by not the reciprocal, the converse. I'm going to put a little subtitle in here of what the thing is supposed to be. I can't remember the right name, but we want to multiply by the thing that is going to turn the numerator into a rational number, and it'll mess up the denominator, but big whoop. Hopefully it'll clean up our polynomial so that we can plug in 4, do direct substitution, and figure out what our limit is. So I'm going to multiply the numerator by exactly what it is. Hey, why would you do that? I don't want you to do that. I want you to do this. Yeah. X plus 5. Oh, but we're not going to copy it perfectly. We're going to turn it into a plus. So we're going to keep everything the same except for in between those two terms. We're going to do the opposite sign. So this one was a minus, so I'm going to turn it into a plus. If it had been a plus, I would have turned it into a minus. So now we have the limit as x approaches 4. In the numerator, we can just square those two terms, the square root of x plus 5 and the 3, and slap a minus in the middle. So square 3, oh, it's 9. If we square the square root of x plus 5, we end up with x plus 5. And we're going to make a right mess of that denominator. So in that denominator, you know what? It's just going to be such a mess. So I'm going to keep it like this. I don't want to FOIL all that. It's just going to make a mess. So let's just not do anything with it right now. Because I don't want to make a mess. Who wants to make a mess? Don't make a mess. I've been playing this game over the summer, and this lady keeps yelling me to not make a mess, but then also tells me to make a mess. It's weird. That numerator turns into x minus 4. It is path of exile, for those curious. All right. Now, those two x minus 4s, they'll cancel each other out. Oh, sweet, which is good because it's that x minus 4 that was preventing us from doing direct substitution. So now we have the limit as x approaches 4 of 1 over the square root of x plus 5, 3. Why would you write a 3? That's not the number I want. I want a 5. All right, get a little space down below. And let's do our direct substitution now, because hopefully we can plug that in. So we get 1 over the square root of 4 plus 5, so that's the square root of 9, which is 3 plus 3, which is 1/6. Dunzo. All right, now, last example. This is a tricky one. So I go to direct substitution. Doesn't work because I can't put 0 in the denominator. Okay, great. Well, let's factor. I can't factor sine. Okay. Well, let's multiply sine in order to turn it into a rational. Sine's already irrational. So if we can't do that, what are we supposed to do?
I'm not sure. I'm afraid we need to use math.
Well, we're going to use the sneaky limit from the beginning. Now, I'm going to jump to the end because then you can see it faster. We have this real sneaky limit. They've given us some special tools at this point. We'll probably talk about them more later, about where this comes from. If you want, there's proofs. We're going to use this sneaky limit in order to figure out what we've got. If we can get a sine x over x, we know that limit is 1 as x approaches 0. We're just going to accept that as fact. So if we can get that, then we'll know what the limit is. So we've got that 5. That 5 is the only thing that's screwing things up. But remember from last time, if the limit is being multiplied by something, we can take it out. So I'm going to slightly rewrite this as the limit as x approaches 0 of 1/5 times sine over x, sine x over x. Since that's being multiplied, I can take that 1/5 and jump it in front. So this goes, woo! So now we have 1/5 times the limit as x approaches 0 of sine x over x. And we're accepting as fact the limit as x approaches 0 of sine x over x. That's just a special fancy limit that we just sort of know. It's just 1 times 1/5. Well, that's 1/5. Na-na. Cool. I'm going to do one more sneaky one. I might cut this up a lot just for time, but I wanted to show you this one because it's a little sneaky. We want to try to get that sine x over x, but we've got tangent. Well, we know that tangent is sine over cosine. So we can take that tangent. We're going to really split this thing up. We know we definitely want a sine x over x. But we need that to be that sine x to be a tangent. So we know tangent is sine over cosine. So if I multiply this by 1 over cosine, this sine x and that cosine x, you want to picture this as a big tangent. So now we've done one of our tangents, but this is tangent squared. So we have one more tangent to deal with. Now all this, checking the limit, as x approaches 0. Break that up into pieces. Our first limit, sine x over x, that's 1, times the limit as 1 over cosine approaches 0. 1 over cosine of 0. We can just direct substitute that. So that's 1 over 1. Cosine of 0 is 1. Tangent, again, we can direct substitute that. Tangent of 0 is 0. Right? So that's 0. So we get 1 times 1 times 0. So this thing is 0. The tricky thing is that initial step where you have to take that tangent and break it up into a sine and a cosine. But once you do that, you get a nice sneaky limit at the beginning. And then these two, you can direct substitute and then just multiply all those limits together. And those are all of our texts for today. So we've got our numerical limit and direct substitution, which we kind of talked about last time, factor cancel, rationalize, and then our special limit. There's a couple other ones that might show up in your practice examples, and we can do some in class. So, yeah, bye-bye.